This conceptual question allows you to put together the ideas of both torque and rotational inertia. So first of all, we have 5 different situations. We have 2 masses on opposite ends of a rod, and each of these rods is going to be rotating about its center. And we're going to try and find which of these rods has the largest angular acceleration. And so this depends on 2 things. First of all, it's going to depend on the net torque. And the torque is going to be the perpendicular component of the force times the distance from where that force is applied to the axis of rotation, which is the center of the rod. And it's also going to depend on the rotational inertia. So if 2 things have the same torque, the one that has larger rotational inertia will have a smaller angular acceleration. So the first thing that I'm going to do is I'm going to calculate the rotational inertia of each of these objects. Rotational inertia for a single mass is that mass m times its distance from the axis of rotation r squared. And if we have more than one mass, like we do in these cases, it's the sum of the individual masses times their distance from the center of mass squared. So in case A, we have two 2-kilogram objects, so the rotational inertia for one of the sides, for the left-hand side, is going to be its mass, 2 kilograms, times the distance from the axis of rotation. And if the rod is 2 meters long and it's rotating around its center, then that distance is 1 meter squared. That's the rotational inertia for the left-hand side, and I add to that the rotational inertia of the right-hand side, which is also 2 kilograms times 1 squared. And so this gives a rotational inertia of 4 kilogram meters squared. Finding the rotational inertia in case B, if we look at it, it's the same 2-kilogram objects each 1 meter away. So this one will also have a rotational inertia of 4 kilogram square meters. In case C, we have different masses. We have 4 kilograms that are on the same 2 meter long rod. And so this is going to be 4 kilograms times 1 squared plus 4 kilograms times 1 squared. So that's going to be 8 kilogram square meters. If I look at case D, it's 2 kilograms. It's on a 4 meter long rod. So the center is 2 meters from either of those masses. And so the rotational inertia is going to be 2 kilograms times 2 meters squared plus 2 kilograms times 2 meters squared for the other side. And so we get a total rotational inertia of 16 kilogram square meters. And in case E, it's the same situation. So we have 16 kilogram square meters again. So we've calculated the rotational inertias. A and B both have a rotational inertia of 4 kilogram square meters, C is 8, and D and E are 16 kilogram square meters. But that's only part of this. We also need to look at the torque. So the torque is going to be R times F perpendicular. That's the torque due to one force. So if I look at each of these rods, on each of these rods, all of the forces are going to be making this rotate counterclockwise. So on each one of the rods, I have a counterclockwise torque due to one force and another counterclockwise torque due to the other force. And so my net torque is going to be both of those torques added together. So in case A, my net torque is going to be 1 Newton times 1 meter plus 1 Newton times 1 meter for the other torque. So those are my 2 individual torques, and that gives me a net torque of 2 Newton meters. In the second case, my net torque is going to be 2 newtons times 1 meter plus 2 newtons times 1 meter. So it's going to be 4 Newton meters. In case 3, my torque is exactly the same as it was in case A. It's 1 Newton times 1 meter plus 1 Newton times 1 meter. So I get a net torque, again, of 2 Newton meters. In case D, my torque is 1 Newton, and that distance from where the force is applied to the axis of rotation is 2 meters. So it's 1 Newton times 2 meters plus 1 Newton times 2 meters. So it's going to be 4 Newton meters. And then in case E, I have a force of 2 newtons, but it's acting at a 30-degree angle. And so what we care about is the perpendicular component of the force. And so I need the vertical component of those forces. That's the component of the force that's perpendicular to the r vector, which points from the axis of rotation to where the force is being applied. And so that y component is 2 newtons times the sine of 30 degrees, or 1 newton. And so we can look and see that case E is identical to case D. The torque is going to be 4 Newton meters. And we can also see that case D and E are both going to be the same angular acceleration because it's the same torque and the same rotational inertia. So that's going to be the final piece. We need to find the angular acceleration of each of these. And so in case A, the torque is 2 Newton meters. The rotational inertia is 4 kilogram meters squared. So the angular acceleration is 2 over 4, or 0.5 radians per second squared. In case B, the angular acceleration is 4 divided by 4, or 1 radian per second squared. In case C, the angular acceleration is 2 divided by 8, or 0.25 radians per second squared. And again, we said D and E are both going to be the same. So if I just do this really quickly, the angular acceleration in case D is 4 divided by 16, which is also 0.25 radians per second squared. So both of those are identical. And so D, E, and C are all 0.25 radians per second squared. A was a half of a radian per second squared. And finally, B is the largest angular acceleration of 1 radian per second squared. So this is just like when you're looking at forces. You can't just look at the largest force acting on objects to figure out which one has the biggest acceleration, because it also depends on the mass.